Hi everybody, welcome to video 2 of your snow lecture series. What we're going to be talking about now is using something that we've actually created in a previous part of this chapter, specifically epoxides, and we're going to be using them as substrates that we can crack open and act as electrophiles in SN2 type chemistry. And so it turns out that there are two different ways you can use epoxides as substrates in substitution reactions. The first one is under basic and neutral conditions. So we'll title our note 6A, basic and neutral conditions. The second way in which this works is under acidic conditions, and we'll get to that in a second. So under basic and neutral conditions, you can take an epoxide, which just remember is this three-membered ether ring, also known as an oxyring, and we're going to take some sort of nucleophile. I'm just going to keep this generic for now. And then we're going to treat this with an acid source in the end. Any old acid source would do. Typically these don't even have to be terribly acidic. Usually a solution of something like ammonium chloride would end up working. And what this is going to do is it's going to crack open the epoxide ring, creating our carbon nucleophile bond, so nuke, and then our oxygen in the end is going to be protonated, creating this substituted species where we have a nucleophile essentially 2 carbons away from our formed alcohol. Kind of cool. It turns out though that this is not really the type of reaction that winds up working on all ethers. So for example, if I was going to, instead of using this ethylene oxide here, if I was going to use diethyl ether, and I ran the same sort of reaction, so specifically I treated this with a nucleophile, two comes after one, not B, some sort of acid workup, what we're going to see is that there's just nothing going to happen. And so the reason for this really disparity in these two different types of reactions is the thermodynamics of what's happening here. On this type of reaction, what we're doing is we're creating a carbon-carbon or carbon nucleophile bond, to be a little bit more generic, and we're creating an oxygen-hydrogen bond. These wind up being two very stable species, and they help push this reaction downhill. It turns out, though, that if this was to work here, we do the exact same thing. So what gives? Why does this wind up giving us an open product where we're breaking a carbon-oxygen bond when this doesn't? And the long and the short of this is that this electrophile here is essentially spring-loaded. You can think of an epoxide as suffering from the same type of ring strain as a cyclopropane ring. Your orbital overlap here is really not great. And so because of that, it really has a desire to spring open and make its bonds go from 60 degrees where it's stuck here to really these optimized 109.5 degrees that you'd expect for an sp3 hybridized normal tetrahedron. And so that's what makes these types of epoxides in very short and small rings be relatively reactive when compared to their acyclic ether intermediates here. Okay, and so there's a couple of interesting things we can do with epoxides. So I'm just going to shift to the other side of the board. But before we do that, we're going to have to cover the mechanism. How does this wind up working? And so, to be a little bit more specific here, I'm going to go ahead and give you what the nucleophile is in this reaction. And so, we're going to use sodium hydrosulfide, so NaSH, plus ethylene oxide. And we're going to run this in a polar aprotic solvent. Something like DMF, something like DMSO is a great way to work here. And so what's going to wind up happening in this case is that first we're going to mix. So first step, mix our reagents. And then second step, we're going to treat this with a little bit of acid to protonate everything in the end. And so in doing this, I'm going to use dilute aqueous HCl, just so we're a little bit more specific in our reaction here. So the way in which this is going to work is that the lone pair of our nucleophile is going to do backside attack on our epoxide here, cracking that epoxide open. And in doing so, we're going to create an alkoxide intermediate with a negatively charged oxygen. So our sodium's just still chilling in solution. And we've got our O- here. So what's going to wind up happening then is that when we add a little bit of acid in solution, so this is dilute aqueous HCl, remember that aqueous HCl is really a mixture of H3O. And chloride and water, because HCl is a very strong acid, will dissociate upon contact with water. This is then going to supply the extra proton to our alkoxide to create our neutrally charged product here. And so using this, you can quickly envision the fact that, okay, as long as I can control what my nucleophile is, this gives me the opportunity to make all kinds of really interesting carbon-carbon and carbon nucleophile bonds that are 2 carbons away from an alcohol. And this winds up being a very important tool in our synthetic toolkit when we start trying to create things like pharmaceuticals, pesticides, or molecules with a specific material science interest. Okay, so I'm going to leave it there for this video. Where we're going to pick up next time is regiochemistry of addition to epoxide. So specifically, what happens when your 2 sides of your epoxide are not the same? Which side does your nucleophile add to and why? Stay tuned.